Okay, welcome everyone. I hope you all had a good evening and are well rested. We're going to kick off today with the second half of Liam Balents' talk on quantum spin liquids, Majorana edge modes, and thermal Hall.
Thank you. Okay, that's everything.
And you have your thing on?
Oh, yeah, let me switch it. Yep.
Okay, now I'm mic'd. Great. Okay, so today we have to really get to business. Right? Thanks for showing up so early. So last time I tried to give kind of very broad overview of quantum spin liquids, and today we're going to focus down. I talked mostly about wave functions and a little bit about more general theoretical descriptions of quantum spin liquids. Just to remind you that these are kind of very highly entangled states. And in some cases topological. We talked about how to express kind of representative wave functions of these states in terms of projections of fermionic partons. We were infinitesimally away from making a more general point, which is that one of the probably the most interesting aspect of these states is that they have very exotic excitations. That entanglement allows them to support emergent, I'm going to say fractional. A better, kind of more general word I would like to use is non-local excitations. By such excitations, I mean these are excitations that could never exist in a finite collection of spins. Non-local means that a single one of these excitations, bless you, could not be created by a local operator. It can only be created by non-local operators, or local operators can only create them in numbers bigger than one, pairs, for example. An example of that in the context that we were talking about would be spin-ons. In this RVB cartoon, you can imagine just kind of superimposing valence bonds, but leaving some spin out. And this extra spin, a state like this is an excited state, that we haven't put as many spins entirely into singlets. It's actually kind of a non-local state, because to create this state out of the ground state, I have to rearrange really an infinite number of valence bonds. I have to sort of unpair this electron, which would have been paired with something else. Therefore, I have to move those valence bonds. I do that really badly. Over here, I have to move that valence bond somewhere else, etc. And in fact, it takes you have to actually apply something like a string of operators to create a single one of these spin-on excitations. And then in the wave functions we talked about, we could think about this type of excitation as something, we talked about making a ground state, taking some kind of fermion ground state like a semiconductor or a superconductor and projecting it. We can imagine adding quasiparticles to that superconductor and projecting that state. And that would be a kind of variational wave function for the spin-on. So indeed, in those states we described by these variational wave functions, these spin-ons could be fermions. And that's already a weird and surprising thing for a spin system, which is basically entirely made out of commuting degrees of freedom far away. So fermions can emerge. Just an example that you might be familiar with, and if you're not, I'm not really going to explain it, but we'll get to something similar, is Kitaev's toric code model, which is actually basically the same topologically as a Z2 spin liquid, and actually the same RBB state, that has these topological phases have a kind of simpler classification and a simpler understanding. These excitations are basically tabulated. And that, in the toric code, there are 3 of them. There's a particle called the electric and magnetic particle, and then there's a third one, sometimes called epsilon particle, which is basically kind of bound state of E and M. And these have certain statistical properties where, for example, if you take a E particle and move it adiabatically around the M particle, the wave function of the system changes sign. These kind of description of these particles, rules for what happens if you bring them together, and what happens when you take one around another. These are the kind of fundamental descriptions of a topological quantum spin liquid like this. Right, many of you, probably most of you, have seen this. Okay. But the focus today is going to be on a more specific, much more specific question. Broadly speaking, I'm interested in the question of how do you actually detect quantum spin liquids? So, with this understanding, this is kind of the striking aspect of quantum spin liquid states. We should be trying to detect these emergent particles. Okay. The problem is exactly that these particles are non-local. Often it's very difficult to detect them. Our standard method to detect excitations in quantum systems, in materials, is to do some sort of scattering measurement. Scattering measurement might be is adding or removing energy or particles from a system. We always do that. We do that with light. We do that with neutrons. We do that with electrons. In all those cases, we're really looking theoretically at some response function, response of the system to some local operator. And that local operator can never create a single one of these non-local excitations. So, yeah?
This isn't philosophically different from a Fermi liquid and particle pairs, and those are very non-local objects in space.
But in a Fermi liquid, we have ARPIS.
Okay.
So we can add a single electron to the system. Or we can do a tunneling measurement.
Okay.
Those directly detect the electron spectrum. If we want to look, indeed, the challenge is, suppose we didn't have that, then we have to deduce the existence of electrons and holes from measuring optical conductivity or other transport. We're lucky they're charged, so
Right, exactly.
we can do a lot of
Yeah.
things with them. Okay.
Yeah. But philosophically, they're still entangled and non-local.
Oh yeah. Well, they're not non-local because we can because we have electron operators, so they're physical. Okay. Okay. So there's no general answer, and many spin liquids we don't know how to do it, but there are a couple of examples where at least there are some striking signatures. So I'm going to focus on one particular one for almost all of this talk, but maybe quickly mention an example where we could do a spectroscopy. So this example 1 is actually this U1 quantum spin liquid in 3 dimensions. Okay. And that sounds kind of abstract, but this is a spin liquid state which is predicted to exist in some of these what are called quantum spin ice materials, and some being hotly studied now. A couple of recent papers on praseodymium hafnate, praseodymium zirconate. These are just particular materials with some rare earth spins. This particular spin liquid state has something which is not true for any of the 2-dimensional spin liquids, which is that it has an emergent excitation, which is not really non-local. It's emergent, but still is something that can be created its quanta can be created one at a time by physical operators, and that's the photon. So for that particular state, photon of light. If you write the low energy Hamiltonian, it's really you have a sum over momentum and polarizations. There's some velocity, some effective velocity of light, mod k times. Those are the excitations of the system, and you can really, we understand enough about these models that we could actually predict the structure factor. This is just the spin-spin correlation function. It has a term in it which has some kind of spectral weight in it. It's a delta function of omega minus c effective k. And importantly, this weight is proportional to modulus of k. And then there's a bunch of smooth stuff, continuum. So most 2D spin liquids only have continuum scattering. Okay, but this is different. If you think about electromagnetism, we have both particles and the gauge field itself. And the photon is kind of the quanta of the gauge field. The particles only give continuum. What we would call a spin-on only give continuum scattering, but this is something that's... So this is, in principle, is a smoking gun signature that could be looked for. It looks a little bit like a Goldstone mode in an ordered magnet, but the spectral weight is wrong. Goldstone mode, this actually diverges like 1 over k at small k, whereas our photon goes to 0 like this. And it's very robust. You could break all symmetries of the system, which for any magnon mode would open a gap. This doesn't. So hasn't been seen, but people are looking for it, and there are thermodynamic signatures of that. Unfortunately, those materials are very challenging because basically the effective exchange constants here are around 1 Kelvin. So any experiments to see these things are really millikelvin, maybe microkelvins. So very hard. So the rest of the talk, I want to focus on another example. Which is basically Taev's non-abelian chiral quantum spin liquid. Okay. Which maybe might be present in some materials like alpha ruthenium trichloride in the B field. And this is really motivated by some recent experiments that came out. You can find them on the archive. I'll cite them. Okay. So let me start by reminding you of, again, I imagine most of, well, it's all theorists in here practically, most of you have seen Kataya's famous honeycomb model. So it's on a honeycomb lattice. It involves spin 1/2 Pauli matrices at every site, and what he did was divide the bonds into 3 orientations. We call them this orientation is X orientation. This orientation is Y. And this is Z. There. Okay. So on the bonds that are oriented in the X direction, the X components of the spins interact. On the Y direction, the Y components interact. And on the Z components interact. I first saw this model in a talk that he gave in KITP around 2003. I think he wrote his paper, eventually wrote this thing many years later, 2009 or something. It was, most of us didn't even know who Kitaev was at that point. He was kind of an unknown guy coming from nowhere doing quantum computing somehow. And suddenly, I've been working on spin liquids. This guy comes in with this exactly solvable model that people were arguing whether they could even exist, and here it's a completely solved problem. Actually more exotic than most of what's anyway, amazing guy. So he showed us not only this model, but let me call this JK for Kitaev. Okay, showed us how to solve it. So what he did was to take the spin operator and express it in terms of 4 Majorana fermions. So these C's are Majorana fermions. So they obey this anti-commutation relation. They're Hermitian, so the Hermitian conjugate of C is C. And here you can take mu to also be 0. Well, that one will be 0. Mostly I don't want to write the 0 because it makes the equations ugly. So this is a bit like the parton representation of spins I introduced before, where you write a spin in terms of 2 complex fermions. If you think about the counting, a complex fermion can be expressed as 2 Majorana fermions, has a real and imaginary part, basically. So that's 4 Majorana fermions. This is also 4 Majorana fermions. You have to impose some constraint, and there's a constraint. Way to impose that constraint is that suppose that this combination of operators equals 1. Maybe he wrote it like this. Okay. So then what you can notice, you can plug this in here. Okay, then this doesn't look like it helps. You get a 4 fermion Hamiltonian. But having written it, one can notice that this Hamiltonian actually has a bunch of conserved quantities. Let's see, how do I do it? I'm going to just erase this. This is where my Blackboard skills failed. Clearly, I should have chosen the Blackboards better. Oh, I can go faster. Go a lot faster. Good. All right. So you can define an operator that lives on a bond. Okay. So every one of these bonds is a type. It's either X, Y, or Z. And on that X, Y, or Z bond, I'm going to take the product of these fermion operators that are of that same type. Okay. This, having plugged that in, you can check that Uij actually commutes with H. Then it's possible, so we can basically treat these things as constants. Okay, they're square to 1. So the Uij squares to 1. So we have some choice of values we can take for them, but they can be simultaneously diagonalized with the Hamiltonian. And then we write, having taken that, the Hamiltonian can be written as some coefficients Aij times Ci, Cj. You notice this only involves the X, Y, and Z fermions. The 0 ones are left out. Okay. Where Aij is Jij, Uij. Okay. But these are constants. J is just Jk. Okay. Good. Okay, so having written this and knowing that we can treat this as a constant, now we have a free Fermion Hamiltonian. We can actually solve it. All right. Now, the ground state energy of this Hamiltonian is going to depend on the choice of these Uij's. Okay, it turns out, okay, that the ground state occurs for configurations like Uij equals 1 everywhere. Actually, the Uij's are, bless you, not entirely physical. They're not invariant under that constraint. There's a physical combination which is sometimes called W. So these are operators defined on the plaquette. Let's say that central hexagon over there. They're equivalent to the product around the hexagon of this Uij's. And this actually has a physical expression in terms of spins. It's something like sigma I x, sigma j y, sigma k z, sigma l x, sigma m y, sigma n z, where these are the sites that you go through cycling around the hexagon. And you should, for example, take the x site to be the site which has an x bond pointing out of the hexagon. So these are called plaquette operators. Since they're built up of the U's, they also commute with H, and these are physical. So these are, we would say these are not gauge invariant. These are kind of like gauge fields. And this is a flux. Okay. But anyway, in the ground state, let's just focus on the ground state, we can take this, so the Aij's just become constant, and this just becomes a constant hopping. I mean, I should warn you, these are antisymmetric, so we have to choose a sign convention. The sign convention can be that I is on the A sublattice of the honeycomb and J is on the B sublattice. All right. There are two kinds of excitations in the model, these bulk excitations. One excitation corresponds to choosing different values of these U's. So these WP's are physical. There's one type of excitation, which is to take, for example, WP equal -1 on some plaquette. You see, they're all +1 in the ground state. This is called a flux excitation. And this has a gap. The other type of excitation is the Majorana Fermion. To see how that behaves, we have to diagonalize that Hamiltonian. So how do we do it? Well, we can go to momentum space. Okay, so H, since A is a constant, we just write this as ijk. Let me be a little bit more explicit. Sum on I on the A sublattice, and sum over mu. Mu would be the three directions, so the three bonds around it. Ci, Ci plus mu. Okay. That's a very explicit way to write the Hamiltonian. Okay. And now we know it's translationally invariant, so we should go to momentum space. So the way to do that is to introduce the usual kind of decomposition like this. So the honeycomb lattice is a lattice with a basis, so we need to keep track of the basis. So S would be A or B, labeling the two sublattices, and I sum over momentum. Ci is for mission, so the dagger of this has to be equal to itself. That's why this coefficient is C dagger. But that also means that if I take the term, if I change the sign of K, I have another term that has exactly the same form. So this summation is kind of redundant. If you count the number of degrees of freedom, I do this on a lattice, the number of momentum points will be equal to the number of sites, number of unit cells. But if I only have one Hermitian operator here and I have one complex operator here, I have too many operators. So the way to do this, well, there are different ways to handle it, but basically what I'll do is I'll divide the Brillouin zone and take only half of it. I'll take the Brillouin zone, it's not a square. Brillouin zone looks like this. So we'll take sum over momenta with kx positive and all ky. That's a legitimate way to count the right number of degrees of freedom. Okay. So now you can take this and plug this in here. Okay, and the answer is kind of quite familiar. It looks, at this point, a lot like solving graphene. Bless you. One can write the Hamiltonian. It's a little algebra. Sum over K. CK dagger times a matrix. CK. So the matrix is in the space of A and B sublattices, okay? Because the hopping is always between an A and a B sublattice. So this is hopping from a B sublattice to an A sublattice site, and this is vice versa. And again, this is a sum only kx positive. And this function f of k is something like 2I j Kitaev sum on mu big I k dot the unit vector, however you normalize it, vector connecting one site to its neighbors. So this is a complex function. This is basically a free fermion Hamiltonian. It's going to have energies which are plus minus the absolute value of f of k. And so the ground state, the many-body ground state, consists of filling all the negative energy states. And the low energy excitations occur when this is approximately 0. So those 0 energy excitations, they happen when f of k vanishes. And that occurs at the Brillouin zone corners. So here, here. These points are equivalent by reciprocal lattice vectors. So usually in graphene you get then 2 Dirac cones. Okay, but here, one of the Dirac cones is not physical because only half the K states are physical. Okay. So there's just one Dirac cone. I'll try and plot the energy. A single Dirac cone. And we could bring it out, we could write CK alpha as psi of k plus k, big K, alpha, where k is that wave vector. And then one would find, if you expand around so to linear order, Fourier transform back to real space, so that's a k. Hamiltonian Fermion has this Dirac form. Okay, should be kind of familiar from graphing.
Question?
Yeah.
What is this, the empty band with respect to the C? What is that represented in terms of divisional spin variables?
Oh, these are highly non-local things in terms of spin variables.
So it's not thinkable.
Not very, no, I don't think so. So we can understand, one can go back and ask the converse question, how are the spin variables expressed in terms of the C variables? Okay, that's a better question, a more answerable question. Although the C variables are very non-local, so they don't have a nice expression in terms of the spins. The spins, conversely, they can't create a single one of these fermions, but they can create pairs. So remember, the whole construction started by writing this. Okay. So somehow we lost this entirely. That went entirely into these UIJs, and hence into the Quanta variables. And this is these are the variables we're working with. So it turns out if we actually act on a state with this, what happens is that we create one of these Majorana fermions, and we create some fluxes simultaneously. Okay. So the simple spin excitations are like that. That's for a more involved model. If we start perturbing Kitaev's model, spins can also create pairs of Majorana fermions.
But I guess you need to know that if you want to think about, say, neutron scattering or something
Absolutely.
of a material that realizes this.
Absolutely, yeah. But I'm not going to talk about neutron scattering. That leads down the path towards broad spectra continua, which are very hard to distinguish. But there has been a lot of work on that. It's interesting. So this is a single two-dimensional Dirac Fermion. Dirac Fermions are, we're kind of familiar with them from graphene, and we know they're only stable if we impose some symmetry. This gapless Dirac Fermion could develop a gap. I probably shouldn't use sigma here. In my notes I use tau. Let me try to switch to tau. It's not the same thing at all. I mean, this is the sublattice. This basis here. We could add a term like tau z psi, and that would open up a gap with some coefficient, call it m. This doesn't happen in Kitaev's model, and the reason is this is actually odd under time reversal. So if you break time reversal symmetry, for example, by adding a magnetic field, generically this term appears. And Kitaev showed how it occurs in perturbation theory in a specific direction of magnetic field. But generically, we believe it almost always appears in a generic direction of applied magnetic field. Okay. So if that happens, we have, let me write the first quantized Hamiltonian in K-space. That develops a gap. And it looks like spectrum becomes, this is where, again, I suffer because you're not going to be able to see it once I move the board. Just shouldn't use that board. All right, that's fine. So it looks like this. Okay. I'm destroying this, Rich. It's like Mardi Gras or something.
It's my fault, I dropped it.
You dropped it.
Yeah.
You dropped it back there. Okay. So this process of let me rewrite that Hamiltonian. This might look kind of familiar, this massive Dirac equation. It comes up in lots of places. It comes up in the study of the integer quantum Hall effect and Haldane's model. Again, in that case, that's where you get multiple copies of this because you have multiple Dirac terms. It also arises very directly in a spinless P plus IP superconductor, where this Hamiltonian would be the one that describes the transition between a weak pairing and strong pairing state, actually. So one of the things that's well known about this Hamiltonian is that the change of sign of M.
Did you mean tau by the sigmas?
I did. Tau equals sigma for the purpose of this lecture. Thanks, yeah. The change of sign of M changes the Hall conductivity of these fermions of psi by 1 unit of E squared over H. Now that's not a physical thing. These are not actually charged particles. But it does have an implication that if we have a boundary, have a region here with M, let's say less than 0 and M bigger than 0, at that boundary there will be an edge state. Chiral edge state flowing in some direction. Okay? That's just like an integer quantum Hall edge state. I don't know how familiar that is to people, but let me, this is not an easy thing to arrange, okay? This, you can kind of imagine we would attain this, M changes to minus M under time reversal, so we have to apply one sign of magnetic field in one region of space and another sign of magnetic field in another region of space. Let me show you roughly how that works, okay? I'm not sure if the students are familiar with it. Are you familiar with this? So maybe not all. I'll never get a straight answer.
You need eye clicker.
Sorry?
You need eye clicker for honest answers.
Yeah. They have that upstairs. Okay. So let's actually solve this problem. Okay. They call this the x direction and this the y direction. And I'm going to take my Hamiltonian. I'm going to write the Schrodinger equation here. Get rid of this line. I'm going to need more space. And I'll let M now be a function of y. This acts on psi, and will equal some energy times psi. So I'm looking for solutions of this equation. In particular, I'm looking for bound states to the domain wall. I know that this region where y is equal to 0. I know that the states far away I can approximate by plane waves, and they'll have a gap. So there could be a bound state in here. And I'm just going to make a guess. I'm going to choose psi. So psi is a spinner, right? If you wanted to put indices on it, there would be index like that. Okay. Psi is a spinner, and I'm going to choose psi to be an eigenstate of tau x. I'm going to choose it to be the eigenstate with eigenstate plus 1. Just going to make that guess. And this should be a tau z. Z is squared. All right, so then there's a nice property of Pauli matrices that tau y is, let's see, tau x, tau z. Tau x times tau y, tau x times tau z is I tau y, so I should put a minus I here. That's an identity for Pauli matrices. So with this assumption, tau x acting on psi gives psi. So I can write the first term as minus IV dx. Tau y I'm going to rewrite using this. So I have minus I times minus I gives minus v tau z tau x dy. And then I have plus m of y tau z acting on psi as epsilon psi. Still as a function of y. But now tau x acting on psi is 1, so I can erase this. There's no x dependence, so I can take this to be an eigenstate of momentum in the x direction, so this becomes vkx. Okay, so now if you examine this, I have I'll move the vkx to the right-hand side. I have tau z times minus v dy plus m of y psi equals epsilon minus v kx psi. So this equation will be solved if the left-hand side is 0 and the right-hand side is 0. So I'm going to set this equal to 0 and this equal to 0, and I can make the left-hand side 0 if I just solve this equation. I need minus v dy plus m of y psi equal to 0. And so that's a linear equation. It has a simple solution. Its psi is proportional to e to the integral to y dy prime m of y prime divided by v. So if you differentiate that, you get the derivative of this and pulls it down. Okay. So this will be you notice it's an exponential. So the argument of the exponential is actually going to grow because far away from the interface m it goes to a constant. So this will either grow or decay exponentially as a function of y. And I've chosen it here so that m is negative above the positive axis and positive below. The sign change is absolutely crucial. That enforces that this thing decays exponentially in both directions. Okay. So this decays like e to the minus m over v absolute value of y at large. So this is a fine, good bound state normalizable solution, and it has this equal to 0, so energy equal to vkx. So this is a chiral edge state. It has all positive velocity. The big one. Let's go with this one instead.
I have a question.
Go ahead.
It looks like from this analysis, it looks like it's an edge state between two boundaries with different topology.
Yes.
Here both sides is topological trivial actually, because n doesn't depend on k. The n is a constant, it doesn't depend on k. Then if you calculate the 1D number or something, the n axis doesn't go to the minus the region. So the n
You actually can't. You would like to try to evaluate some Chern number or something. You actually can't do it from the Dirac model alone because it's not periodic in the Brillouin zone. So you would need to. I've made a linearization. So if you really want to evaluate it, you'll need to actually evaluate and extend to the full Brillouin zone. Both sides are topologically non-trivial. You have to be a bit careful. This is actually not something that ultimately fits in the scheme of non-interacting topological insulators. Now I'm not going to explain it in full detail. I'm just going to give you a little bit of an argument. Okay, but you put your finger on a very important point that this is an interface between two topological things. So the result of this analysis is that there's a boundary Hamiltonian. Let's say call it plus minus is some edge state. We actually can sum over all kx because kx is an expansion around the Dirac point. Vkx times some bound state wave function psi kx tag or psi kx. And if we were to write this in real space, this will look like. So this is a chiral 1D Dirac Fermion. This is just like an integer quantum Hall edge state. And this is actually the edge between, exactly as you pointed out, actually between two different time reverse copies of Kitaya spin liquid. Okay. Now that's a really hard thing to achieve. What we could achieve is a boundary between, experimentally, is Kitaya spin liquid and something trivial like the vacuum or a normal insulator. So what I want you to imagine is separating out this interface and splitting it apart into some region with a vacuum in
So
between.
before you do that,
Yeah.
so when you say it's hard to experimentally achieve, so you said the M came from a magnetic field.
Yeah.
And so if I have a magnetic field gradient, that's not sufficient to do this.
It'd be possible, but it would be that magnetic field. So what do we know? I'll get to it eventually. I haven't really talked about it. In Kitaya's ideal model, one could do it. It would be a gradient that goes through zero. Indeed. Okay. In experiments, actually, there's a problem, which is that in real materials, there's magnetic order intervening at low field. So that to achieve these states, if it's possible at all, we have to go to a field above some threshold. And so if we try to do this, we have a mess in between. And we don't want these, we'd have very large scale gradients. Maybe in cold atoms you can do this in solid. We don't want anything on these super long length scales. But actually it's more interesting if we don't, okay? So we can always write a Dirac Fermion like this. Where's my nice stuff? We can write a Dirac as two Majoranas. By writing psi is eta 1 plus I eta 2. There might have used some other normalization. I don't know. For some reason I used 4. I have no idea why. You can plug these will be Hermitian operators unlike psi. You plug that in, we'll get that H plus minus can be written as H plus H minus, where H1 plus H2, where H1, Hi is just integral dx minus IV over 4. This 4 can't be right. Let's make it 2. That's probably 2. Exercise to the audience to get the 3 factors right. They don't matter. All right. So there's no longer dagger that doesn't exist for eta. So this is a Hamiltonian of a 1D chiral Majorana Fermion. I think I'm going to write MF from now on. Oh, when very long. Okay. So I'm just going to assert without proof that what actually happens here is that each of these boundaries has a single chiral Majorana Fermion. Okay. In momentum space, this looks okay. In momentum space, it looks rather weird. Because eta is like a real field, its Fourier transform and k and minus k are related to one another. Basically, it contains half the modes of this sum, so it only has modes at positive k. That's what this Hamiltonian looks like in momentum. So you might be tempted to draw energy versus momentum dispersion like this, but again, remember, this half is fake. Yeah?
So even without proper proof, can we physically motivate that even without a n greater than 0 region, we'll still have a chiral mode?
Oh yeah, well, so it's not, you can't get rid of this chiral mode, so this is this is we can always write this as two co-propagating Majorana modes. So this is just an exact statement. This is equal to this. And now you could ask, can I ever gap out these two Majorana modes? You can't, because they're co-propagating. This is very common wisdom from integer quantum Hall effect. You can never remove these modes. And if you look at Kitaev's paper, you could see, I've just done a hand-waving argument, but you can actually derive it for the case of an interface to a vacuum.
But can you state that they're localized on each of the edges, or are they kind of buzzed over?
No, they're localized. They'll be this is the vacuum, so that obviously they're not going in here.
I see.
It's very similar to the derivation. They have to be localized. There's a gap here, so there can't be any states at zero energy in the gap. They decay exponentially if they're localized at the boundary. You can really find them explicitly for that model. It's a bit more of a lattice calculation, so not quite as nice. So this actually, Majorana Fermion is an example of that may be familiar from statistical mechanics. That's actually the low energy field theory for the Ising model. So this is actually the chiral Ising conformal field theory. The central charge. It looks very simple because it's free fermions. But lurking behind this free fermion description is some deeper, more subtle mathematical structure of the Ising model. And we can kind of guess it because the original Kitaev solution not only had Majorana Fermion excitations, it also had these vortices. And the vortex actually, so there's I don't have time to talk about this, but basically there's this phenomena of bulk boundary correspondence, this one-dimensional, 1 plus 1 dimensional conformal field theory that describes the edge, also describes the quasi-particles, the anyons in the bulk. So there's a Majorana Fermion excitation in the bulk that corresponds to this Majorana Fermion at the edge. There's another operator at the edge, which is part of the Ising field theory, which actually corresponds to the spin operator in the Ising model. And that corresponds to the vortex in Kitaev's model, which in this gap phase becomes a non-abelian anyon. From the point of view of this presence of a Majorana edge rather than an integer quantum Hall edge is a smoking gun signature that cannot exist in any abelian topological phase. It's a guarantee that this is a non-abelian topological phase. And so this is actually a non-abelian Ising anyon phase. You might be familiar, you might have heard about this because Microsoft is spending hundreds of millions, I don't know, billions of dollars trying to develop Ising anyons in a totally different way from superconductors and semiconductors and quantum wires. Great. All right. So, how might we observe this? So this is an observable thing. It's a low energy excitation. It's an emergent excitation. It lives at the edge of the sample. We can hope for some phenomenology that's somewhat similar to quantum Hall effect. So there's a recent experiment. And I can tell you, I wrote down the archive number. It's somewhere here. 1805. This is and they study this material alpha ruthenium trichloride, which is believed maybe to be somewhat close to Kitaev system, people calling it, among other materials, an example of a Kitaev magnet. It has a phase diagram which is kind of known, at least the classical phase diagram is known. It forms an ordered antiferromagnet in low field, and then there's a phase boundary here. This is a pretty low temperature. This is something like, 7 Kelvin. 7, 9, I can't remember. Sorry?
7.
7. I haven't lost it completely yet. I should say the belief is that J Kataev here is something like, I don't know, maybe 80 Kelvin, some number. Estimates differ, but somewhere around there. So it's, more than a factor of 10 bigger than this. Nevertheless, we know the Kataev model wouldn't work, so something else is clearly present. I won't talk about what the actual description of this material is, so let's say that people don't really know. But this happens at a pretty small field. Depends a lot on the orientation. These guys are measuring at some angle like this, kind of 30-degree angle to this direction, and the in-plane component of the field, I think, is about 6.5 Tesla here. Again, this is a very small field compared to this Kataev scale. But basically, you should know that for a spin 1/2 magnets, typically 1 Tesla equals 1 Kelvin, basically, in terms of Zeeman energy. What they observe, so the saturation field here is some huge field, I don't know, hundreds of Tesla. But there's a region in here where they see something unusual. And what they study is, let me draw a cut across here. They measure the thermal Hall conductivity. So they take that one's not good. Take a sample like this. They run a heat current down it, and they measure temperature differences using 3 probes along the x and the y direction. And from this, assuming they do the usual analysis, that say the current, this is the heat current, I'm going to drop that. Heat current is some tensor times the temperature gradient. And if you assume that Jy is equal to 0, okay, because the heat can't escape the sample, then by measuring these temperature differences, you can deduce the conductivities. And they observe, if they plot cap xy divided by temperature versus magnetic field, they observe something like this. This is again this H parallel between, let's say, 7 and 9 Tesla. This occurs at temperatures between maybe 3 Kelvin and 5 Kelvin. And this value here is tantalizingly close, really very close to pi over 12 AB squared over H bar. So this quantity is the quanta of thermal conductance, just like E squared over H is the quanta of electrical conductance. So let me derive that. So why is this is an exciting number? It's actually what you would predict for Majorana fermions. So there's a kind of standard analysis that goes like this. Let me think about my 2 edges. So I imagine that my top edge is at a temperature T top, and my bottom edge is at a temperature T bottom. If the temperature is different at the top and the bottom, there's going to be more heat here than here. Let's say this is bigger. All the heat here is transported to the right. All the heat here is transported to the left, so there'll be a net heat current. So we can try to compute the heat current just at one edge. Let's imagine we'll look at I as a function of temperature T at the top. So this is going to be, remember we have the Hamiltonian here. Let me write the sum. We have to sum over all the states. The heat current will be the velocity times the energy of the state times the occupation, which will be a Fermi function, and we want the current, so we should divide by this is the number, so we should divide by the length of the system. So in the large system limit, this is the integral dkx over 2 pi from 0 to infinity. Okay? And that's because, again, from this fact that kx is positive. This is v squared kx, and this is the Fermi function e to the beta v kx plus 1. So we can at least see the form pretty easily. You can rescale kx to make this argument x. So let me define kx is, let's call it x, divided by beta v. Okay, so then we have v squared times kx squared. Each factor of is going to be integral dx x. The v's will cancel here, and we'll end up with 2 inverse factors of beta, which is just t squared. And I'm running out of room here.
You want to use the whiteboard? Just
Oh.
continue on to the right?
Good idea. Great. So we have our 1 over 2 pi, and we have t squared. Okay, there's some kb. I said kb equal to 1. I should put kb here. Times 1 over e to the beta x plus 1. This integral, there's no beta, sorry. So this integral actually is some well-known integral. It's pi squared over 12. And one of the pi's cancels, so we get pi over 24. Okay. Now you can worry about units. I've mixed energy and frequency. Okay. The real energy is not VKX, it's h bar VKX and some other h bars. Proper units has a h bar over here, because you can understand, because current is energy, heat current is energy divided by time. So 1 kBT is energy, and then we need to know 1 over h bar to convert the other one to time. Okay. So this is the current. Now the total current, this would be the top current. The total current is I top minus I bottom. So this is pi over 24, kb squared over h bar, t top squared minus t bottom squared. We're studying, if we want to study conductivity or conductance in linear response, these should be close to one another. So this is approximately 2t times tt minus tb. So in linear response, this gives pi over 12 t kb squared over h bar times delta t in the y direction. So now you can see this answer, which is actually exactly what's measured in this experiment. So this is the predicted quantized thermal Hall conductance. Okay. Yeah, I know, I've run out of time. So I haven't been able to explain that. How much time are you going to give me? You give me 5 more minutes?
5. We have 1 hour.
Okay, 5 minutes.
5 minutes.
I'll hold you to it.
How about 10 minutes? Give me 10 minutes. 10 minutes is better. Okay. So that's pretty exciting. But one might worry about one thing. And let me just explain that worrying, which worried me for quite a while until we did a calculation, and I realized that it actually works out. It's kind of amazing to me that it works out. Let me give you the citation since I don't have much time. I'm only going to be able to sketch how this works, but you can read our preprint. It's a beautiful experiment. It's very striking. Hasn't been reproduced, so okay, we can all worry about that. But as a theorist, I worry about another thing, which is in the experiment, cap xx is actually approximately 1,000 times bigger than cap xy. If you're familiar with quantum Hall effect, the usual quantum Hall effect, we only see quantization when sigma xx is actually much, much less than sigma xy. Okay. And it's kind of understandable from this edge state picture. If you think about this calculation we did, I told you actually that the temperature at the top was T top and the temperature at the bottom was T bottom. And I assume that the temperature of both edges are actually constant in the x direction. Okay. And that's because there's no scattering there. There's no way for it to change, nowhere for the energy to go. But if kappa xx is very big, it means that in our Hall bar, we're running a heat current like this. Basically, the temperature isotherms are almost like this. The temperature gradient is mostly like this. This is the gradient temperature. The temperature is not constant at the edge. Okay. So actually, the derivation is not applicable. Okay. And it's kind of worse than that. So there are two ways out you could imagine. One thing you could imagine is, well, okay. And so what's probably true, what the experimentalists say, we believe that's reasonable, is that kappa xx in this experiment is mostly due to phonons. This is mostly due to the lattice. Almost all insulators, it's true. Heat conductivity is mostly due to the lattice. There's just so many degrees of freedom in the lattice, swamps everything else. That's not necessarily so important, but then you can imagine that, well, maybe there's an edge here, and the edge is contributing kappa xy, and the bulk is contributing kappa xx. But again, we still have to explain why the edge is an isotherm when the bulk isn't. So, if you accept that, say that sounds reasonable, then it means the edge is not in equilibrium with the bulk. So, what temperature is actually the edge at? You have no idea. And most likely, most of the time, an experimentalist is measuring temperature just by making contact with the sample. It's probably measuring the lattice temperature, not the fermion temperature. So that explanation would not hold water. Okay. So what we set out to do was to ask, what do we really expect? Okay, fully expecting that we would have a calculation that shows that the experiment can't be right. Okay. And so what we did was just construct a little model. We modeled both the edge. Actually, we even modeled the edge over here, where the contacts are. Okay. And the bulk. So we have some phonons in here, and we have Majorana fermions at the boundary. And let me just give you, there's a quantum analysis, let me give you the classical analysis. Basically, pretty much classical. So there's we could have let's imagine in general we have a temperature for the fermions, and we have, which is a function of x. Let me talk about the top edge. And we have a temperature for the phonons, which depends on x and y. And these control the currents. So there'll be a heat current. This is the fermion current, okay, at the top edge. And it has to obey a continuity equation. So the heat current at the top edge, if the fermions were completely decoupled from the phonons, in the steady state, the divergence would have to be 0. This would have to just be constant, so dxi would be 0. However, in general, it can actually get some, it doesn't have to be 0 because energy can be transferred from the phonons to the fermions. And in general, they're coupled. And actually, by continuity, this current, the heat injected is just the heat current coming in from the phonons. So that's the Y component evaluated at the surface. And then in the bulk heat current, there's no edge state there, so it should just be 0. Now, we need some more ingredients, so we need kind of constitutive relations. So we can say that, well, we know how the current is related to the temperature. So we'll say that the current here is actually this, in linear response, it'll be the quantized value of kappa xy times kind of the temperature difference from equilibrium of the fermions. Derivative. Let me write it like this. It's better to write it. Pi over 24. Go to units where the quantum is 1 t squared. And then J is minus kappa xx times the gradient. This is T fermion of T phonon. So the phonons don't have any Hall conductivity, of course. And this is kind of, the ingredient here is that this is now a function of x because now heat can be transferred to the edge. In general, it's not a constant temperature. And we need one more ingredient, which is kind of a boundary condition on the curve here, okay, if you think about it. And that depends on how the fermions and the phonons are coupled. Suppose they were decoupled. If they were decoupled, the boundary condition would be that the heat current coming in from the outside is 0. So actually, this quantity is related to the strength of the coupling. There's some coupling constant times T phonon minus T fermion that appears here. So the way to think about this is, imagine we didn't have any currents. We just were studying a time-dependent situation. We start with some initial state where there's a different amount of energy in the phonons and the spins, but everything is uniform in space, and we just let it evolve in time. The spins and the phonons will come to equilibrium. If the phonons are hotter, they'll transfer energy into the spins, into the fermions. If the phonons are colder, they'll transfer energy the other way. And this is just the rate of that transfer. This is a basically complete set of equations that describe the system. And you can study them in linear response. For lack of time, you can read about this in the paper. It's not hard. It's actually quite easy to do, taking both the top and the bottom edge. And you find a surprising result. I need to say one more thing about this length lambda, this parameter lambda of t. So this describes how strongly the phonons and the spins are coupled. And basically this goes like some positive power of temperature. For a simple model, I think it's probably a reasonable model, it actually goes like the 6th power of temperature. Okay, large power. And the reason is it's difficult to couple this chiral edge state and the linearly dispersing phonons. There's not a lot of phase space to do that. So at lower temperature, they actually couple worse and worse. This is actually kind of well known in spin systems generally, that they couple badly at low temperature. Associated with lambda is some kind of equilibration length, which you can sort of read off this equation. It's basically lambda, I guess it's kappa xy quantum divided by lambda. So the smaller lambda is, the less coupled they are, the longer a system has to be for the edge and the phonon to thermalize with each other. So we can sort of plot the behavior of the system as a function of temperature, or equivalently lambda. Both in lambda increases as I increase temperature, or 1 over this length, L. So when temperature is high enough, actually, the coupling between the phonons and the Majoranas increases. Okay, so we're in a situation where the There's a couple of characteristic temperatures. The important one is here, where, how did I write it? I'm nicely writing it. Let me write it, think of lambda, this is, if lambda is bigger than this, the ideal quantized thermal Hall conductivity divided by the length of my system, then the edge is mostly in equilibrium with the phonons. And so the original derivation of the quantized Hall conductance is wrong, okay, because the temperature is not constant at all of the fermions. However, so this is a surprising result, okay, this is kind of where we expect to be. In this whole region, if you don't measure the fermion temperature, which is what you assumed in that derivation, if you measure the phonon temperature and use that to interpret the Hall effect, then you observe a quantized thermal Hall effect. Okay. It's kind of bizarre. So what actually is happening is the thermal current is actually not being carried by the edge anymore. Really, the current in the bulk is doing something like this, flowing at some, that's exaggerated, it's mostly flowing like this, tiny angle. Okay. And that's, that current is flowing into this edge and out of this edge and causing the temperature to be non-uniform in the edge. But it conspires to be that, so this fact that the current in the bulk flows at an angle looks as though there's a bulk thermal conductivity, Hall conductivity, even though there isn't. It's getting imposed by boundary conditions at the top. And that effective thermal Hall conductivity actually equals the quantized one. The prediction is that if I decrease lambda, including lambda in this regime, then the quantization fails. And this is actually lower temperature. So, you know, we're used to, in quantum Hall effect, the lower temperature you get, the better the quantization gets. So the prediction is here actually that you go too far, you will disequilibrate the Majorana edge and the phonons, and the quantization will be destroyed. Okay, it's not been seen, but so, you know, to my surprise in this analysis, we kind of ended up concluding that it's possible they're observing something real in this experiment. I didn't have enough time to explain this, but it's a kind of fun. You have enough here to solve this. It's not too hard, actually. Kind of this is like a Jackson problem.
Excellent. Well, let's thank Leon. I want to take a couple questions if there's any, especially from students. In the back there, yeah.
So the power of alpha equals 6, is that a phenomenological parameter or?
No, so I don't have time to explain it. It's so we took a model of Majorana fermions at the edge, coupled to phonons, and did a calculation of that. You can use Boltzmann equation because fermions are quasi-particles, well-defined quasi-particles, and phonons are well-defined quasi-particles. So you can do this within a Boltzmann equation and find the rate of transfer. So this is for a model of a disordered edge. You have some disorder to relax momentum conservation. It's larger than, I made a comment, is even for integer quantum Hall edges, you will get a pretty large exponent, but not as big as for Majorana fermions. The reason is that integer quantum Hall edges, most edges, also for, if you try to do this type of thing for topological insulators, the edges, they carry well-defined fermions with a well-defined charge. And so the charge can couple to the phonons. Majorana fermions don't have a well-defined charge. There's no charge density to couple to the phonons. can only couple to kind of the velocity, local velocity of the Majorana.
All right, with that, why don't we thank Leon one more time?